So today we're talking about derivatives with exponential, logarithmic, and trig functions. You guys are going to, of course, just like the other day, you're going to learn how to find the derivatives of these special types of functions. Okay, so we're away from the polynomial functions for the moment, where we use a lot of product rule, quotient rule, chain rule, basically the power rule just fancied up. Now we're going to look at exponentials and logarithmic and trig functions. Okay, I do believe every single one of these is in your reference booklet. Minus like maybe one or two that I have up here, but I've only put them up here just for kind of just to make sure that you have them physically, or that you can visually see them. So let's start though by reviewing just a little bit of exponential functions. This is a great time to jump back into the functions unit because IB stretches beyond just, hey, here's a question solely on derivatives. Part A could easily be asking, hey, what is the y-intercept of this exponential function? And then it could actually find the derivative. So we can't forget about those basic things. So what is the most simplest form of an exponential function? No, not linear. No, that's a quadratic.
Is that a linear?
Oh, that'd be a to the x.
It would be a to the x, okay? Because remember, it's called an exponential function because your variable is in your exponent. Okay, now realize that could be anything from like 2 to the x, or 1/2 to the x, or 4 to the x. All these are examples of exponential functions. But every single one of these exponential functions has a y-intercept located where?
The 1.
Be a little more specific.
The 1.
At 1. Because think about it, to find a y-intercept, don't you plug in
0 for x?
0 for x, and then realize that 2 raised to 0 power is the same thing as what 1/2 is raised to 0 power is the same thing as what 4 raised to 0 power is, which is 1. So every single one of these has a y-intercept at 0, 1. And last but not least, every single one of these functions have an blank in its graph. An asymptote. What type? We have 2 different types.
Wait, hold up.
It has a horizontal asymptote, okay? Don't forget that exponential functions, they are asymptotic to the x-axis like so, or like so, depending on if they are a number bigger than 1 or a number between 0 and 1. Of course, negatives means they're reflected over the x-axis, and so then they'll be below. But every single one of these is like this. Don't forget about some of these basic things. Of course, we'll review them, but we cannot forget about them as well. To find the derivative of these exponential functions, first off, you have e to the x. The derivative of e to the x is e to the x, okay? Simple as that. However, if you do have something that's other than e as your base, the derivative of a to the x, so such as like 2 to the x, then the derivative of it is going to be a to the x times the ln of a. So all you have to do is recognize, okay, well, what's a in this case? 2. So then your derivative would just be 2 to the x ln of 2. Both of these, the one at the top and the one in the middle, both of these are in your reference booklet, so you don't have to worry about memorizing them. This last one is not in your reference booklet, but it's more so just so you guys can realize that, 2 to the x is like your most basic of exponential function that they could give you. But they could also give you an exponential function where the exponent is also a function in itself, okay? So an example like that would be 3 to the 2x minus 1, and you're asked to take the derivative of it. A would be 3, your base, the function is your exponent. And so in those cases, it's pretty much, you're gonna have to do chain rule. You're gonna have to do chain rule with this, where you take the derivative of basically of the function, which is this part, and then you multiply it, which I'm missing a multiplication symbol, by the derivative of your exponent. Okay? So if this is my example, my base is 3, my function is my exponent, then the derivative of this would be 3 raised to the 2x minus 1 times the ln of 3 times the derivative of your exponent, which will be what? 2. Now here, we wouldn't be able to simplify this anymore because 1, we cannot multiply 2 and 3 together because 3 is being raised to the 2x minus 1 power. So then that would be our derivative. That's as far as we could go. Mm-hmm.
Oh, why is the x the why is it so?
Why does it stay the same thing?
Yeah.
That one is beyond me at this point. It's like one of those I was like, I'll take every little bit that I can get.
Why do you like?
All right. So let's find the gradient function for y. Y equals to all of these. Remember, anytime you see gradient function, that basically means what?
Derivative.
It means the derivative. So basically, find the derivative of each one of these functions. Use your rule, give it a try, and then we'll go over these.
Oh no.
Mm-hmm. Yep. All right, so we're finding the derivative of a. That's 2e to the x plus e to the negative 3x. Remember, the sum and difference rule basically says when you have multiple pieces added or subtracted from each other, you just take the derivative of each individual piece. So take the derivative of 2e to the x. What does that become? 2e to the x. Remember, this is nothing but 2 times e to the x. It's a constant multiple rule. So you leave the constant how it is. You take the derivative of e to the x. Luckily enough, it's just e to the x. However, for e to the negative 3x, we're going to have to use what?
We don't know. Would you
Well,
like e to the negative 3x times ln of e times the derivative of the
times the derivative of the function. Now, yes, you can use that last rule there. What's the ln of e? So this goes away, so it's just negative 3e to the negative 3x. You can also use chain rule here. You can use chain rule here. Your outside function is e to the x. Your inside function is negative 3x. So if you use chain rule, you'll take the derivative of the outside. What's the derivative of e to the x? But remember, with chain rule, you don't write x, you write the inside function, and then you multiply this by the derivative of the inside, which is, and essentially that's what you're doing here when you apply that rule, that last rule. It's just a tad bit shorter. So you can use chain rule for this because it's a function within another function. Like if I do the composite of e to the x and negative 3x, I'll get that function. The plus or minus?
The negative 3. No, not negative. And the exponent.
No.
So when you write the answer for it, it would just be negative 3 times e to the negative 3x.
Yep. Because this is a constant that's being multiplied to this function, so those usually go in the front. For the next one, what rule on top of the rules from the other page do I have to use here? Product. I have 2 functions here. I have e to the x and I have, I have x squared and I have e to the negative x. So remember, product rule says what in general? Plus the other way around. So it's the first times the derivative of the second plus the second times the derivative of the first. So if I'm trying to find the derivative of this entire function, I need to do the first function, which is x squared, times the derivative of the second function, e to the negative x. What is the derivative of e to the negative x? We can plug it into the same rule that we plug this into, or we can recognize that it's another chain rule.
I mean, it's always a chain.
Yep. So what's the derivative of e to the negative x? Negative e to the negative x. Again, you have two functions. You have e to the x and then negative x. I'm plugging negative x into the x of e to the x. So when I apply chain rule, I take the derivative of the outside. What's the derivative of e to the x?
One. No.
E to the x.
Yeah.
But I don't write an x, I write the inside function. And then I multiply this by the derivative of the inside. What's the derivative of negative x? Negative 1. That's how it becomes a negative e to the negative x.
Wait. I mean.
If you want to use this rule, that's fine. You can.
Yeah. But when you plug it into chain rule, it looks like you keep the exponent over the e.
Yes.
You multiply it by the coefficient.
Yes. Well, it's not always the coefficient. Just depends on what the exponent is.
Yeah.
But no matter what, it's always you take the original and you multiply by the derivative of the exponent. That's what it is every time, or an exponential function.
Got it.
Every single time.
All right. Yeah.
Okay? Plus the second, which is e to the negative x, times the derivative of the first. What's the derivative of x squared? 2x. So then our final answer for the derivative so big. It's going to be negative x squared e to the negative x, because there's nothing but a negative 1 in front, plus 2x e to the negative x. Remember, constants usually go in front of bases with exponents. That's why I moved the 2x to the front, and that's also why I moved the negative to the front of the x squared. No need to go an additional step to try to factor out e to the negative x out of both terms, or even an x out of both terms, if you're just finding the derivative. Okay? You just, you continue to keep going when you don't have to. And for the last one, what rule am I going to have to use here? Quotient. So that is low times the derivative of the top. What is the derivative of e to the 2x? 2e to the 2x. Very good. Minus the top times the derivative of the bottom. What's the derivative of the bottom? All over low, x squared, low. So then that becomes 2x e to the 2x minus e to the 2x all over x squared. Again, no need to factor out e to the 2x from the numerator because it's not going to cancel out with anything in the denominator, which means I'm just going to end up having I'm doing extra work when I don't have to, especially if I'm just finding the derivative. Now, maybe later when I have to do things with the derivative, we might need to, it might be helpful, but right now, we don't have to do that. Let's take a look at these. We are finding dy over dx of these functions here. These are different because they're exponential functions, but their base is not e. Their base is the actual number. So this is where that formula for the derivative of a to the x, ln of a, comes in handy. Okay? Again, that's in your reference booklet. What would be the derivative of 3 to the x using this formula? And that's it. Can't do anything else beyond that. That's it. But for b, My exponent is an actual function, x squared minus x. So this is where I'm going to have to apply the chain rule, okay? I take the derivative of the outside function, which is basically a to the x, so it's going to be this entire bit here. But I don't write an x, I write the inside function, aka the exponent. So this becomes 5 raised to the x squared minus x, ln of 5. Then I have to multiply this by the derivative of the inside. What's the derivative of the inside, aka the exponent? And that's my derivative. That's my final answer. I can't go any further than that. Nope. If I distribute, I'll be doing like that little bit extra that I don't have to do. I mean, you can distribute the ln of 5 because everything's being multiplied together. Yeah, it's not gonna make a difference whether you distribute it or not. Questions? Seeing up? No idea. With natural logs, which remember they are the inverses of exponential functions, e to the x. If you have y equals ln of x, the derivative of that is 1 over x. Of course, x has to be greater than 0 because we cannot take the natural log of a 0 or a negative number. And of course, because we can't take the natural log of a negative number or 0, that means it restricts the domain of the derivative as well to just being greater than 0. We're going to find the gradient of these two functions. Now, do realize this incorporates multiple rules in one, but just to make sure that everybody has a very basic one. If I have ln or 4 times the ln of x, the derivative of that would just be 4 over x. Because again, 4 is a constant. So it'll be 4 times 1 over x, which just becomes 4 over x. Those are your simple ones, okay? That would be SL. Let's take it up to HL, okay? Where they incorporate multiple rules in one with these functions, okay? When I look at this one, I have the ln of 1 minus 3x. Huh? You would, not quotient,
Change?
you change.
Never mind. Keep going.
you would do chain because you have, what's your outside function, what's your inside function? Those are your two functions. So we know that the derivative of ln of x is,
1 over x.
but I don't write the x, I write the inside function. Then I need to multiply this by the derivative of the inside, which is 1 minus 3x. What's the derivative of that? Negative 3. So then I just multiply. My derivative is negative 3 over 1 minus 3x.
Huh.
Because it's the same thing as just saying negative 3 over 1. When I multiply fractions, multiply straight across. What about B?
Product.
Product rule. My first function is x to the third. My second function is the ln of x. So I do the first times the derivative of the second. What's the derivative of ln of x?
1 over x.
Plus the second
Ln of x.
times the derivative of the first.
3x, the ln of 3? Or no?
3x squared.
Where's it going? Got it. Got it. Oh, no, sorry.
What?
I thought it was, give me a second. Give me, I gave it your saying. I
Okay.
get it now.
So first times the derivative of the second, plus the second times the derivative of the first. I do need to multiply and simplify here. X to the third divided by x is just an x squared. And then here, I'm just going to bring that coefficient to the front of the ln of x. And there's my derivative for this function. You had them switched?
I said 3 to the x, or that's what I was visualizing. Oh, okay. I'm sorry. Well,
X
where
to
you
the
going?
third, X to the third.
No, that's.
Oh, wait. It looked like there was.
Yeah. Okay.
Questions on ln?
Whenever we're showing our answer, whenever we do limits when on each step we have to put limit when h goes to 0. Whenever we're doing this, do we have to say like the derivative of x equals?
It's good. It's good to do, especially if you have a whole sheet worth of like work. It distinguishes that this is my final answer for the derivative.
One thing I was like, are the onions gonna be like still gonna happen?
Right now, they're still good for the end of the year.
Oh,
Yeah, they haven't said otherwise yet.
I don't want the only thing to happen here is supposed to be my IDA.
I agree. Maybe not for the class, but I'm just saying in general. It was very stressful last year. Let's take a look at these. A little bit more involved. Okay? Do these ones with you. Differentiate with respect to x is the same thing as saying what? Find the derivative. Just in a different way. So I have y equals the ln of x times e to the negative x. Okay? Well, this here is an example of, or this here I'm going to have to use what rules to work this out? Chain, product, and of course I got the natural log and the exponential in there. Okay? So I do the chain rule. I have my outside function, which is the ln of x, and my inside function, which is this whole setup. So I take the derivative of the outside, which is 1 over x, but I don't write an x.
Right. X e negative x
Very good.
times
Then I have to multiply this by the derivative of the inside, where I have to use product rule. So the derivative of the inside involves product rule.
x times negative
The first times the derivative of the second,
e negative x times 1.
plus the second times the derivative of the first. Very good. Now mind you, all of this that's in that second parentheses is all over 1. So when I multiply it together, I'll get negative x e to the negative x plus e to the negative x all over x e to the negative x. Now that's a lot of e to the negative x's. Actually, every single term has an e. So we can actually simplify this some more. Now this is where simplifying is going to pay off because I can't. Something in the numerator cancels out with something in the denominator. If you can't see it, again, both terms have an e to the negative x in common, which leave me with the negative x plus 1. So I can cancel out that e to the negative x. So my final answer, my derivative of this function is just negative x plus 1 over x.
Oh, that's so cool.
So this would be an example of where we could just simplify it.
It becomes more simple by canceling out that e to the negative x.
But if it doesn't become more simple,
Don't do it. Because everybody you factor it out, but then you put the inside wrong. You know?
It's just that don't do it.
For B, I'm gonna need a little bit more space, so I'm probably gonna hop over to the next page.
Oh, that one was.
Challenge.
That one doesn't look to me.
All right. Online, how we doing? For this one, you said it's like product, quotient, and chain.
Yep.
There's actually that's true. You could do, of course, chain, because you got the outside function, and then the inside would involve quotient rule, which would involve a product because you have x plus 2 times x minus 3. Now, you could make this a tad bit easier on yourself by doing what? I can FOIL, so then it takes out the product rule, and it's just chain and quotient. But there's something else you can actually do that's a little bit more simple. It involves your laws of logarithms.
Oh.
Think back, your laws of logarithms. Remember when we used to condense and expand using those rules?
Oh, yeah.
When it was division, if I wanted to expand that, it became what? Subtraction. Okay, so then this became the ln of x squared minus the ln of all of this.
Oh my God.
And because these are being multiplied together, I can continue to expand it some more by doing what here? Addition.
Yeah.
You can do addition. So this becomes the ln of x squared minus the ln of x plus 2 plus the ln of x minus 3. If you notice, I have parentheses around this entire second part because both of these things were originally in the denominator. So what am I going to have to do to that minus?
You're gonna have to stop.
Distribute. And now instead of doing chain and quotient and potentially product if you didn't FOIL, now it's literally just applying the rule for the derivative of ln with a bit of chain. Okay? So really and truly now it's only chain 3 times instead of chain and quotient together. Okay? And these are actually very simple because these are, this is 2 linear factors in the quadratic. Okay? Again, chain, because you have the ln of x and then x squared, that's my outside function and my inside function. So what's the derivative of ln of x? But I don't put an x, I put a, and then I multiply this by the derivative of the inside, which is 2x, minus, I take the derivative of ln x plus 2. Again, another chain, where this is ln of x, and this is x plus 2. So it's going to be 1 over x plus 2 times 1, because that's the derivative of the inside. And I repeat it again one last time. In my opinion, I think this would have been a tad bit easier than trying to do chain and quotient, because then we would have had a fraction within a fraction, we would have flipped some stuff, simplify a lot, it would have been very messy. But this way, I'm just taking chain rule of 3 individual ln's. So this last one's gonna be 1 over the ln, 1 over x minus 3 times 1. And this very nicely simplifies down to be 2 over x minus 1 over x plus 2 minus 1 over x minus 3. And that's my derivative. There is, though, a derivative for if you have a logarithm. So ln was the special one, but there is an actual derivative for logs to a base that's not e. Because remember, log with a base e is the same thing as ln. So we have a log base a of x. Of course, we cannot take the log of a negative number or 0. That's why a has to be greater than 0. The derivative of that is 1 over x ln of a. So the derivative of a log turns into 1 over x ln of a. Again, this is in your reference booklet. Just like the derivative ln of x, which is 1 over x, is in your reference booklet as well. Okay? I'll let you guys know which ones aren't in your reference booklet, so you know we gotta know. Which, to be honest, is not many. Let me think.
It depends on.
So I'm gonna find the derivative of each of these. I have a basic one, and then I have one that's a little bit more involved. Okay, though, we can do it. So the first one is y equals log base 5 of x. This fits right into the setup here. Okay, the value of a is what? 5. So then the derivative of log base 5 of x is just 1 over x ln of 5. Do you realize that this x is the same x that goes here? So when you look at b, which says y equals log base 3 of x squared minus x, x now becomes x squared minus x, which means in the formula, in the denominator, you're going to have that expression. but this 2 is another chain rule. So once you plug this in, you're also going to have to multiply by the derivative of the inside. Okay, so this is chain rule. You take the derivative of the log base 3 of x part, which becomes 1 over x, but I don't write x, I write the inside function. ln of a, what's a? 3. Then I multiply this by the derivative of my inside. What's the derivative of x squared minus x? So then my derivative becomes 2x minus 1 all over x squared minus x ln of 3.
Look, when we commit,
And I'm in this shit with y'all. Okay? Trig derivatives. Trig derivatives. You don't have to write down all of these. Again, every single one of these is in your reference book. Every single, I think that's so funny how it's segue into this. But yes, it's not just sine and cosine, which is all SL has to know, because at the top 2, y'all have to know all of them. The reciprocals, and you also need to be able to work with the inverses of these as well. So this is them in all of their glory. So let's practice with these. Here we go. We're gonna do x sine x and 4 tangent squared 3x. I stopped putting directions because at this point in time you guys should know we're finding the derivative. So I'm gonna say in another fancy way to basically find the derivative of these functions. That's what we're doing. Find the derivative. What rule am I gonna use for a?
The sign
One product?
Product,
Yeah.
yes. I'm gonna have to use product here because I have 2 functions. I got x and I got sine x. Kind of hard to see, but yes, that's x times sine x. So I do the first times the derivative of the second. What's the derivative of sine x? Then it'll be plus the second times the derivative of the first. What's the derivative of x?
1.
So this very nicely simplifies down to be x cosine x plus sine x. And that's our derivative.
Now the next one.
Now the next one, yes. What rule am I gonna have to use here?
chain.
Yeah, chain.
And not once,
Why?
but twice.
Oh, great.
The reason why is because this can be written as 4 tangent 3x, that whole thing being squared. So it's a chain within a chain. You have your very much outside function, which is the x squared. Then you have the inside for that, which is tangent 3x. But then within tangent 3x, you again have an inside function, which is tangent x. And you have your outside function, which is tangent x. And then you have your inside function, which is 3x. So this is an example of a chain within a chain, because you basically have a function within a function within a function. So the derivative of this, follow me, because I want to do this one. Okay? My 4 is that constant. It just stays out there. Okay? But now I have to do the derivative of the outside function, the very most outside function, which is x squared. That is 2x. But I don't write the x part, I write the inside function, which is tangent 3x.
Then you multiply it.
Then I have to multiply that by the derivative of the inside. Well, the inside is again another chain rule. This is another chain rule. So I take the derivative of the outside, which is tangent x. What's the derivative of tangent x?
You can square it.
Secant squared x.
But
But I don't write an x, I write the inside function, which was 3x. Then I have to again multiply that by the derivative of the inside, which is just 3. And that is using chain rule, within a chain rule, to get the derivative.
oh, okay.
Now from here, I just need to simplify. The only things I can multiply are the 4, the 2, and the 3. So it's 4 times 2 times 3.
Six.
I was getting there.
24. So that'll be 24 tangent 3x, secant squared x, sorry, secant squared 3x. That is our derivative.
Oh, wow.
Yes, ma'am. All right. So we have cosecant 3x. Yes, that is C-O-S-E-C 3x. That's how they do cosecant in your reference booklet. So I don't want you guys to be like, oh, whatever happened to C-S-C? I don't know. Okay, I don't. So here we go. This one, we're going to have to apply what rule?
Chain.
Yep, because of the 3x right there. So we take the derivative of the outside function, which is cosecant x. What's the derivative of cosecant x? Negative cosecant x, cotangent x. But I don't write an x, I write a 3x. Then I multiplied this whole thing by the derivative of the inside, which was the 3x. What's the derivative of that? 3. So then this just turns into negative 3 cosecant 3x cotangent 3x. And that's our derivative. Now, the only reason why it's like that because that is still, yeah. This one, I'm gonna have to do this. 2 chains. 2 chains. All right. Been waiting this entire time to do that. Yes. Come on now. Y'all know it's a good one. And I'm gonna go ahead and make this a tad bit easier by going ahead and changing that square root to a 1/2 exponent because this is a chain within a chain. I have x to the 1/2. That's my most outside function. And then I have, for the inside function, cotangent x over 2. But then within that, I have another chain. I have cotangent x, and then I have x over 2. So I need to take the derivative of the most outside function, which is x squared. What's the derivative of x squared? Oh, it's 1/2. Okay. I'm like, what are you saying? Sorry, it's 1/2. My mistake. Sorry, 1/2. So when I take the derivative of 1/2, that becomes 1/2 x to the negative 1/2. But I cannot have an x. I write what? Cotangent. I write the inside function. Then I multiply this by the derivative of the inside, which is cotangent x over 2. The cotangent x over 2 is another chain rule. So I take the derivative of the outside, which is now cotangent x. What's the derivative of cotangent x? But I don't write an x, I write, and then I multiply that by the derivative of the inside, which is x over 2. What is that? 1/2. And that is with the 2 chains applied. So to simplify this, I'm going to multiply my 1/2s together to get what? 1/4. I'm also going to take care of this negative exponent by bringing it to the, and I'm going to bring it down. Now there's already a 4 there because originally I had a 1/4. So I'm going to bring it down there with the 4. And then that negative cosecant squared x over 2 stays in the numerator. And that is my derivative. Thank you. I did miss the 1/2 power. Because when I brought it down, I made it into a positive exponent and I dropped it off altogether. Don't do that. Your inverse trig functions. Your inverse trig functions. Again, these two are in your reference booklet. Let's practice with them. Here we go. Actually, I have a question. Yes. Let's apply this. Give me that second right now. The point P has a y coordinate pi over 6 and lies on the graph of f of x equals arc tan x over 3. We're asked 1 to find the coordinate of P. Now, first off, we're told that the y coordinate of P is pi over 6. So the only thing we're missing now is what? The x coordinate. But we know how to find the x coordinate if we know what the y coordinate is. What do? You plug it in for y into which equation? The original. Okay, so remember, anytime you're ever looking for like a y coordinate, or if you're looking for the x coordinate, like you can always use the original function to do that if you have one or the other. So we basically have pi over 6 equals arctangent x over 3. Now remember, arctangent is the inverse of tangent. So if I'm trying to solve for x, I need to do the opposite of the inverse of tangent, which is what? Regular tangent. So basically, by applying regular tangent to both sides, I end up canceling out the arctangent on the right-hand side. So now you got to use unit circle knowledge. What is the tangent of pi over 6?
Tangent of pi over 6. Oh my god, it was short.
Root 3 over 3.
Oh my god.
So if root 3 over 3 is equal to the tangent of pi over 6, and I'm trying to solve for x, then that means that x has to equal what value? Root 3. So then that is the x coordinate of P. So my point, or my coordinate for P is the square root of 3 pi over 6. Here we have to know a little bit of circular functions here. Now it says find the gradient of the tangent to y equals f of x at P. And I just talked about this. When you see gradient of the tangent,
You need to find the derivative.
you need to find the derivative. And then once you know what the derivative is, to find the gradient, we have to do what?
You plug in the x value.
You plug in the x value into the derivative. So I need the derivative of arctangent x over 3. Well, if we look at the rules for arctangent, we're also going to have to apply a chain because it's not just the regular x, it's x over 3. So the derivative of arctangent is but I'm not going to put an x, I'm not going to put an x, I'm going to put a x over 3. And then I'm going to multiply that by the derivative of my inside, which is x over 3. What's the derivative of x over 3? 1 over 3. Now, don't simplify this. And I say that because remember, we're looking for the gradient of the tangent line, which means I need to find a value. By simplifying, I'm just creating more work. When I could, at this point, plug in the x value of the point to find the actual gradient, which is what the question wanted me to do. So not only did I combine in this problem derivatives of these inverse functions, but I also incorporated an older concept that we talked about when we first started going over and learning about derivatives. So now it's nothing but a little bit of algebra. Go ahead, algebraically find my gradient. What'd you guys get for the gradient? It is 1/4. Very good. So the gradient at P of the tangent line on this particular function is 1/4. Very good. Very good. And that is how, that is your other special functions, your exponentials, your logarithmic functions, your trig functions, your inverse trig functions, okay? We'll save some practice for later. But again, all of these formulas, these here are in your reference booklet for your inverse trig functions. These formulas here for your trig derivatives All of them are in your reference booklet. You just gotta be careful because the top two, because of how your reference booklet's divided up, the top two are in the SL section, the bottom four are in your AHL section of your reference booklet, because that's how it's divided up. The log one, this one here, this is in your reference booklet. The one for ln of x, that one's in your reference booklet. The one for e to the x, these top two are in your reference booklet. And remember, this one here was just to show you that you are going to have chain rule and product rule and potentially quotient rule in these problems too for these special functions. And that was this section 6-3.